Hello everyone, in this video we are going to look at two key issues of learning and two key problems in machine learning. The two key issues are approximation and generalization, and the two key problems of machine learning are overfitting and underfitting. To start with that of the two key issues, which are approximation and generalization, let's consider a target function y equals f of x plus e in supervised learning. And let's consider a trained model y hat equals f hat of x. Now there are two key issues which are usually conflicting in machine learning: approximation and generalization. When we say approximation, we are intended to measure how well a model f hat can approximate the target function f. And when we say generalization, we need to measure the performance of the model for new unseen dataset or for dataset that is not used for training. In the usual standard statistical models, the goal is to find a model f hat that minimizes the loss or error in the data being used for fitting. However, such a model with a minimum loss or error could not be a guarantee for its performance to new unseen datasets. Therefore, the goal of machine learning is to make a balance between these two key issues, approximation and generalization. Or machine learning aims to both approximate the target function and generalize well for new unseen data. As a result, for this purpose, the entire dataset is usually divided into two sets, a train set and a test set, usually using the split ratio of 70-30%, 80-20%, 90-10%. Therefore, these two splits, train and test sets, have different purposes. The train set is used to train the model of interest, therefore the objective is approximation, and the test set is used for measuring the performance of the trained model for new unseen data. So the test set purpose is for that of evaluating generalization. So in the training set, we need to train a model f hat that best approximates the target function. So here we could obtain training errors. These training errors are going to be minimized. Overall, by quantifying these training errors, the training error can be used to evaluate the performance of the trained model f hat in approximating the true unknown target function f on the dataset it was trained on. And the testing set is used to evaluate the generalization ability of a trained model to new or unseen data or dataset that is not used for training. So here we could have testing errors, and we are intended to minimize these testing errors. So the test set is used to evaluate the performance of the trained model on new unseen data points that are not used for training. So totally, for example, if there are capital N examples in the entire dataset, let's assume N examples are in the training sets and M examples, that is capital N minus small n examples, in the test set. So the training error, which is also called in-sample error, represents the approximation error. And similarly, the testing error or the out-of-sample error represents that of the generalization error of the model. The training or in-sample error can be determined using that of the trained data, but the testing or out-of-sample error represents the expected error over the data generating distribution P. However, this distribution P cannot be known, so the out-of-sample error or the testing error is not directly accessible, but it can be estimated from a test set representing that of the average of the pointwise test errors. Now let's come to that of the two key problems in machine learning, which are overfitting and underfitting. So let's recall again the two key issues of learning, which are approximation and generalization. The approximation is nothing but finding a model that best approximates the target function, and the generalization aims to find a model that has a better performance for unseen or new data. Still, the model could be susceptible to two problems, which are called overfitting and underfitting. We say a model overfitting when the model is so flexible and touches each and every point. So when the model is so flexible, that is, the training error is too small. However, such a model can catch on to spurious patterns. So for such a model, the training error is very low, but for a dataset that is different from the trained dataset, the error could be higher. Therefore, though the training error is low, the test error could be very high. So in such case, the data is memorizing, that's the algorithm is memorizing the training data. So this is not learning. And the other problem is underfitting. In such case, the model is assumed to be too simple to capture the patterns in the training data. It does not reflect that of the true relationship between the inputs and the outputs. In such case, both the training and testing errors would be high. So overfitting is usually characterized by when minimizing the in-sample error leads to a situation where the out-of-sample error increases. Therefore, it becomes valuable to detect the occurrence where minimizing the in-sample error leads to an increase in the out-of-sample error, and at that point, it is essential to halt the training process. So this approach is usually called early stopping, and it is guided by the validation dataset.